Hello, welcome to our class for today. This is Noble Mind Science Tutors Online, and I remain Notable Michael. Please, if you have not subscribed to this channel, please subscribe to this channel and click on the notification button so that when we upload a new video, YouTube can notify you. Also, you can reach us via the WhatsApp number that is showing right on your screen. So, for today's class, we're going to be talking about work, energy, and power. Work, energy, and power. So please, as I've always said, get your writing materials, your calculators, so that we can go right away to our class for today. So I hope you are ready. So let's head straight to our class. Right, so as I said, we're looking at work, energy, and power. So we are going to be looking at now work done. Work done. We From your class, we know that work is said to be done when a force moves through a distance. When a force moves through a distance. So work done is the product of force times the distance in the direction of force. Or you can simply put it as work done is the product of force and the displacement in the direction of the force. So if work done is given by force times distance, and the distance is the displacement in the direction of the force. So in symbol, W is equals to force times distance F times S. And the unit of work is the joule. The unit of work is the joule. And the joule is defined as the work done when a force of 1 Newton moves a body through a distance of 1 meter in the direction of the applied force. So work done can also be expressed as Newton meter. We know that the unit of force is Newton and the unit of distance is meter. So work done can also be expressed in Newton meters. We also want to remember that force is equals to mass times acceleration. From our previous class, you can get that force is equals to mass times acceleration. So definitely work done, if you substitute for force in this above equation, you will see that work done can also be written as mass times acceleration times distance. So for a linear motion, work done can be expressed as mass times acceleration times distance, knowing that mass times acceleration is equal to force. This is equals to force. So work done can also be expressed as mass times acceleration times distance for linear motion. Now, for an object that is under the influence of gravitational force, we know that the force for object that is under gravitational force, the force is equals to mass times acceleration due to gravity g, and so for object under gravitational force, work done is equals to mg times h. Don't forget that mg is equals to the force. So work done for an object under the influence of gravitational force can be given as mg times h. So for object that is lifted vertically from the ground, or for an object that is falling from a particular height, work done is equals to force times distance. And we know that the distance for an object that is falling or that is lifted vertically upward is equals to the h. So work done is equals to mgh. Work done is equals to mgh, where m is equals to mass, g is equals to acceleration due to gravity, and h is equals to the height. G is always given to you to be equals to 10 meters per second squared. 10 meters per second squared. So from what we've discussed so far, you find out that work is done when a force moves through a particular distance. So if you carry an object on your head and you do not move through any distance, there is no displacement, then you have not done any work. you have not done any work because you did not move any distance with that object. You did not move any distance with that object. So work is always done when a force moves through a distance. If the force does not move through a distance, then work is not done. So I know somebody that carries like maybe you carry a block on your head, you stand in one place for the whole day. In physics, it is regarded that you have not done any work. But if you carry a piece of paper that is even weightless and you move to a particular distance, in physics you have done work. So in physics you have done work. So work is done only when a force moves through a distance. But when the force does not move through any distance, work is not said to be done. So we want to take note of that and also take note of the formula for work, right? Take note of the formula for what our work is done when a force moves through a distance. And for an object that is under gravitational force, work done is equals to mgh. Force can also be replaced by ma, knowing that force equals to mass times acceleration. So basically, this is the introduction to work. This is introduction to work. So sometimes when work is done on an object, the force that is causing that work to be done might be inclined to an angle. So work done in some cases depends on the direction in which the force is moving. So if the force is inclined at an angle, then that force can be resolved into two components. So you can actually have the vertical component and then the horizontal component. You can have the vertical component and the horizontal component. So looking at this scenario, this force F is pulling this box through either the horizontal component or the vertical component. So this force can be, just imagine a boy that ties a rope on a play car and is pulling the car along the horizontal direction. Sometimes the boy might decide to raise the car off the ground, which is the vertical direction, or he might decide to pull it along the ground. So work done sometimes depends on the direction in which the force is moving. So as I said, this force can be resolved into horizontal and vertical components. So and we've said that from our previous discussion that work done is equals to force times distance. So in this particular case, if the body is moving through the horizontal direction, then the component of the force is equals to F cos theta. Is equals to F cos theta. So in that case, it means that the work done is equals to the force in the horizontal direction times the perpendicular distance. Don't forget that force is equals to mg. So this can also be written as work done is equals to what? Mg cos theta times distance. Mg cos theta times the distance. Now, if the object is pulled along the vertical direction, then the work done, then the force is equal to F sine theta. F sine theta here, F sine theta. So for the work done will now become the force times distance, and this is F sine theta times distance. Is that okay? F sine theta times distance. So that can also be written as mg sine theta times distance. Don't be confused. This resolution of this force is just for you. You can get this F cos theta and F sine theta by just like drawing a right angle triangle and labeling it properly. Then use your trigonometrical ratios to get all that. That okay? So if this is your theta, and then you have your force, this is your force, and this is the work. Okay, so we know that cos theta is equal to, for the horizontal direction, cos theta is equal to W all over F. So W here will be equals to what? When you do your, make it so you have W is equals to what? F cos theta. Because some of you want to ask me, how did I get F cos theta and F sin theta? So this is just it. Then for the vertical component is for you to put the work done on the vertical axis. So we know that sine is equals to what? Opposite over hypotenuse. So sine theta, sine is equals to this W all over F, same thing. So your W will now be equals to F sine theta. So I hope that explains that, so that nobody will come and ask me, how did I get F sine theta and F cos theta? So for the vertical component, you have this. Then for the horizontal component, you have this. I hope that clarifies that. So as I said, for a work done can actually depends on the direction of motion on the force, and that is what we have discussed here. I hope that is clear. Okay. So we are also going to be looking at work done by an inclined plane. Work done by an inclined plane. This is very important because an inclined plane is like a machine that makes work to be done easily, right? It makes work to be done easily. So for an inclined plane, we have the length of the plane and then the height of the plane, then the angle of inclination of the plane. So the work done in moving a body along the inclined plane is the weight component of the body along the plane times the distance traveled by the body. So the distance traveled by the body is equal to the length of the plane, which is L. The distance traveled by the body is equal to the distance of the length of the plane. So the weight component of this, the weight component of the object along the plane is equals to W sine theta. So in our previous lecture on friction, you will have come across this. So the weight component along the plane is W sine theta, and the distance is equals to L. So the work done down the plane for an object that is sliding down the plane, the work done is equals to W sine theta times the distance. And this is the equation 1, and it's represented by this figure 1. Is that okay? Now, for an object that is pulled up the plane, this is represented by figure 2. For an object that is pulled up the plane from point A to point B up the plane by force P, by this force P, we see that this force P, we have to overcome two forces. One, the weight component of the body down the plane, and then the frictional force that is opposing the motion. I hope you can see it here. The weight component is W sine theta, then the frictional force equals to mu times R, which is normal reaction. So for this force to move this body up this plane, it must overcome this weight component down the plane and the frictional force that is opposing that motion. So this force, we have to overcome these two weights, which is the weight component down the plane, which is W sine theta, and then the frictional force that is working against the force, against the pulling force, which is mu times r. So which means for this particular case, the work done will be equal to W sin theta plus F times the perpendicular distance, L, times the distance, along the plane, distance of the plane, not the length of the plane, L. So work done is equals to W sin theta times F. Then remember that F in this place is equals to mu times r, and that is what I have replaced here. So work done is equals to W sin theta plus frictional force times the distance. So please take note of this equation. This equation is for the work done in moving an object up the plane of an incline, while this is for the body that is moving freely, or that is coming down on the plane. So take note of these two equations because we'll be using them to solve different problems. So these are the two equations that applies for the work done by an inclined plane. I hope that is clear. So we're going to apply these equations. We'll apply them to solve some problems so that we can drive home how to use these equations. Is that okay? Okay, so before we solve any problem, we also look at work done on falling bodies. So for a body that is falling freely from a particular height, the work done is equals to mgh. Mg, which is mass times acceleration due to gravity times height. Mass times acceleration due to gravity times height. Also, for a body that rolls down a hill, the work done is also equals to mgh. So for a body that rolls down a hill, the work done is mass times acceleration due to gravity times the height of the hill. So we will solve some problems so that we'll be able to drive home these equations that we have discussed so far. Okay. So this is a sample question that we need to solve so that we can drive home the equations that we have discussed so far. The question number 1 says that a loaded sack of total mass 100 kg falls down from the floor of a lorry 2.0 meters high. Calculate the work done by gravity on the load. Okay, so when we discussed this, we said that here you are given that mass is equals to 100 kg. You are given the height of fall to be equals to 2.0 meters, and you know that g is equals to 10 meters per second squared. Okay, so we said that work done W is equals to m times g times h. So based on what has been given to us, so you can just substitute into this equation, and so that you now have that work done is equals to 100 times 100 times 10, which is g, times your height is 2.0. So by the time you multiply that out, you are going to have 2000 joules. 2000 joules. Okay. Alright, so this is it. So we can see that actually once you are able to understand the equations, they are easy to apply. They are easy to apply. So work done is equals to force, which is mg times the height, and that gives you 2000 joules. I hope this one is clear and you understand this one. Okay, so we are also going to look at another question. Okay, so this is another one. This one said that a boy drags a bag of rice along a smooth horizontal floor with a force of 2 Newton applied at an angle of 60 degrees to the floor. Calculate the work done after a distance of 3 meters. So looking at what is given to us in this particular equation, we can actually, they give us the force that is pulling the bag of rice to be equal to 2 Newton. Then they give us the distance they give us the distance to be equal to what, 3 meters, and they give us the angle through which the boy is pulling the bag of rice to be what, 60 degrees. So we remember that in our discussion we said that the force, that is the work done, depends on the direction or pull of an object, or the direction in which the force is acting. So in this particular instance, the force is acting along the horizontal line. So we can write that the force along the horizontal axis is equals to, we said that the force is equals to, along the horizontal is equals to F cos theta. F cos theta. So which means that the work done, Fx along the horizontal axis, is equals to F cos theta. Right? So the work done is equals to this F cos theta. So work done is equals to F cos theta times what? Times distance. So let me just substitute the values there so that we can get our answer. Right? So we have the force is 2 Newton times cos 60 degree times cos 60 times distance. Distance is 3 meters. Okay, so which is 2 cos 60 degrees equals to um, 0 0.5. 0 0.5. So check that out from your calculator. Then this is times 3. Okay, so by the time you work this out, you are going to have 3.0 joules. 3.0 joules. Okay, so this is how to apply this equation. So you see how we're able to apply this equation of using the components of the force. Okay, so once you're able to get the force, just multiply by the distance, then you get the work done. Right? So we'll still solve more problems so that we can drive home all the equations that we discuss and to deepen your understanding. Okay, so these are other sample problems. A boy of mass 50 kg runs up a set of steps of total height 3 meters. Find the work done against gravity. Okay, so this one is just direct. They are giving you the mass. Mass is equals to 50 kg. Okay, mass is equals to 50 kg. Then you are giving height to be equals to 3.0 meters. Okay, so and then you know that G, acceleration due to gravity, is equals to 10 meters per second squared. Okay, so your work done is equals to mgh, which equals to 3 which equals to 50 multiplied by g, which is 10, multiplied by the height, which is equals to 3. Okay, so by the time you solve this out or you work this out, you are going to have 1500 joule 1500 joule as the work done by this ball that runs through this set of steps of total 3 meters. Okay, so I believe that you understand what I'm doing, and then it is pretty easy to apply these equations of work done. Okay, so this is another question. A body rolls down a slope from a height of 100 meters. A body rolls down a slope from a height of 100 meters. Its velocity at the foot of the slope is 20 meters per second. What percentage of its initial potential energy is converted into kinetic energy? Now, I want you to understand one thing. At the top of the slope, the body, the energy it possesses is potential energy because of its position at rest. Now, as it rolls down the slope, at the foot of the slope, the potential energy at the top of the slope is converted totally to the kinetic energy. The potential energy is converted totally to kinetic energy. So for this body, we are giving the height of the slope, we are giving height of the slope to be equals to 100 meters, and we are giving the velocity at the foot of the slope to be 20 meters per seconds. Now, potential energy at the top of the slope, potential energy PE is equals to mgh. So g is known already to be equals to 10 meters per seconds squared. Okay, so we can put that into this equation to give you that potential energy is equals to m multiplied by g multiplied by h. H is equals to 100 meters. So this will give us what? 1000 joule. Now this energy is what is converted to kinetic energy at the base of the, or at the foot of the slope. So we can write that potential energy is equal to kinetic energy. All right, now the kinetic energy at the base of the kinetic energy is given, kinetic energy is equals to half mv squared. So we can substitute into this equation. We'll have that kinetic energy at the base of the slope equals to half times m times v is given to us to be 20 meters. So 20 meters squared, that is 20 times 20. Okay, so this will now give us, if you work that out, you have that kinetic energy is equals to or when you divide this into, so you have 200 joule. So this is the kinetic energy at the base of the, and then this is the potential energy. So the question is that what percentage of its initial potential energy is converted to kinetic energy? Okay, so the percentage energy converted is equals to kinetic energy all over potential energy. Kinetic energy all over potential energy times 100 all over 1. So if you substitute into this equation, you are going to have 200 divided by 1000 joule. You know that the m will cancel out, right? The m was not given, so that will cancel out in this instance. So this you can cancel, you cancel this out. So your final answer will be equals to 20%. So the total energy that is converted to kinetic energy is equals to 20%, right? 20%. Sorry, this place is choked up, but just I hope you follow through with the calculation. So what you have is 20%. Okay, so you, for in this particular instance, we first of all calculated the potential energy and then the kinetic energy. Then before we now look for the percentage. If you look at it very well, you find out that m was not given, but finally m cancelled out. Is that okay? M cancelled out finally. Alright, so I hope you follow through with this, and this is quite simple. Okay, we still have one more to solve on this. Still have some more questions to solve on this. Okay, so this one is a load of mass 50 kg is put up a rough inclined plane, inclined at angle 60 degrees to the horizontal. Determine the work done in moving the load to the top of the incline 20 meters high. Okay, so this is another question that we need to look at critically. Here you are giving the mass of the load to be equals to 50 kg. The mass is 50 kg, and the angle of inclination of the plane is equals to 60 degrees, and then the height is given to you to be 20 meters. Okay, so in this particular problem, we are going to first of all apply the equation for moving an object up an inclined plane, the work done. So we said that work done for moving an object up an inclined plane is equals to the components along the plane mg sine theta, component along the plane plus the frictional force, okay, plus the frictional force that is opposing that motion. Okay, so having known this, in this particular case we don't know the coefficient of friction. Okay, so coefficient of friction can be gotten from tan theta is equals to coefficient of friction. So tan theta is equals to mu. So from this one now we can get tan 60 degrees. So check your tan 60 degree, you're gonna have 1.732. Okay, so this is equals to your coefficient of friction. Coefficient of friction is equals to tan theta. So theta has been given to you, so that gives you 1.732. Is that okay? Now you know that the normal reaction arrow is equals to mg cos theta. Please, all this we've discussed when we treated frictional force. Normal reaction is equals to the weight component that is perpendicular to the plane of the incline, right? The weight component that is perpendicular to the inclined plane is your normal reaction. So we know that normal reaction is equals to the weight component perpendicular to the plane. So this is mg cos theta. Okay, so that is normal reaction. Okay, so you can now put that into this equation that we wrote down. Can put all this into this equation so that we have that work done is equals to mg sin theta plus 1.732 times mg cos theta. So now we're going to substitute into this equation so that we'll have that so that the force, this is the force component, so we're going to have that the force that is needed to pull the body. Okay, so this is force, this is force. Okay, so this is force to pull the body up, the force component to pull the body up, force required, because this will be equals to actually the work. This is the force, so for you to get the work done, you multiply it by the distance. Okay, so in this instance we have this multiplied by distance. All right, so work done multiplied by distance. So first of all, we'll look for the force. So the force component to the force required to move the body up force is equals to this part of this equation. So later we'll multiply by d. Okay, so now we'll have that substituting into this equation, we'll have 50 times sine theta, which is sine 60 degree, times 10 times sine 60 degree, which is equals to 0.866 plus 1.732 times 50 times 10 times cos 60 degree, which is 0.5. Okay, so by the time you work all this out, if you work everything out, you will have equals to 433 plus 433. So this gives us 866 Newton. So this is the force. This is the force that's required to move the load up the plane. Now we said that work is equals to force times distance. Okay, so but in this particular case, the distance is the length of the plane. That is the length of the plane. Sorry for my drawing, but the distance is the length of the plane. So, and then this is the height of the plane. Okay, so here you are giving theta. So in this case, you have a right angle triangle. You have a right angle triangle. Okay, so let me draw this triangle clearly so that we can get it. Yeah. Okay, so let me draw this triangle clearly a little bit. Okay, so you have something like this as your right angle triangle. Okay, so you have this to be 60 degrees, and you have the height to be 20 meters, but this you don't know. So the distance, we have to look for the distance, and from your trigonometrical ratio, you have that sine. You have that sine theta is equals to sine 60 equals to 20 over L. So L is equals to 20 over sine 60, and this is 0.866. So by the time you work that out, you are going to have that the distance equals to 23. So if you work that out, we have distance equals to 23 meters. Please just solve that out. So having gotten that, we can now bring them to this equation. Their work done is equals to 866 multiplied by 23. Okay, so if you punch that in your calculator, you're going to have 20,000 joules. 20,000 joules. 20,000 joules. Okay, so this you can also convert to kilojoules. It will also give you, you have 20 kg, 20 kilojoules. Okay, so this is how to go about this type of problems. Please just try to have an understanding of them so that you can apply them when you want to solve any of the question. Try to understand the application of these equations that we discussed so far. Okay, so this particular one talks on how if work done in moving an object up the incline, and we said that that work done or the force that is moving the object up the inclined plane will overcome the weight component of the object down the plane and the frictional force that is opposing the motion of the force. So which means that the total force is the weight component plus the frictional force, then the work done is that total force multiplied the distance, and distance is equals to the length of the plane. Distance is equals to the length of the plane. You saw how we are able to maneuver and go through these processes, and then we arrive at the answer. Oh, that is clear. So thanks. We'll take in your understanding questions. So these are questions that are meant for you to show your understanding of the topic that we have discussed so far. So please try to solve these problems, solve them, right? Solve them, and if you have post your answer on, you can place your answer on the comment section on the WhatsApp number that is showing, that will be showing on your screen, right? Put them on the comment section or on the WhatsApp number that is showing on your screen. I will look at them and see how you're able to go through the calculations, then see your understanding. All right, so thank you. We are almost running on this class now. Okay, so please, if you have not subscribed to this channel, please subscribe, click on the notification button so that whenever we upload a new video, YouTube will notify you. Also, you can reach us through the number that is showing right on your screen. Alright, so thank you so much for your time. I remain Otuwa Michael. This is Normal Science Tutors Online, and we hope to see you in our next class. Thanks.